Greetings everyone, this is Mr. Mullen. In this video I'm going to talk about heating and cooling a substance at length. So we're going to go ahead and get started. First off, I want to define the difference between heat and temperature, which are not the same thing. Heat in chemistry is the total amount of energy in a given amount of material. This includes both the potential and kinetic energy. So if I'm looking at a chemistry solution, based upon how much material is there, there is potential energy stored in the bonds and the kinetic energy stored in the motion of the particles. So the more bonds there are in my substance, the more heat energy there is available. And also is true for the more motion, the more particles moving, the more heat there is in a substance. One little thing I want to add about heat is that heat always flows. The direction of heat flow is always from hot to the cold object. So if your mom scolds you for letting in the cold, you can kindly remind her that, Mother, it's not that we're letting in the cold, it's that I'm letting out the heat. Because heat, energy, always flows from hot objects to cold objects. Now, don't actually say that to your mom. Temperature, on the other hand, is a measure of the average kinetic energy of an entire substance, and we usually think of this as the hotness or coldness of an object. Now, temperature, the amount of material, does not matter. It doesn't matter how much hot iron there is on a stove. Either way, if it's at a certain temperature, it will still hurt me the same amount. Okay, the hotness does not depend upon how much stuff is there. Temperature is just an average measure of the kinetic energy. So if on average the particles are moving really fast, then it's going to have a high temperature. All right, so what I want to do is I want to talk about energy a little bit more. Some of the common units for energy, the standard unit is the joule, and lowercase j or uppercase j, and a joule is also defined as a Newton meter. And so we said, the other day that work is equal to force times the distance, and a unit of force is a Newton, and a unit of distance is a meter. So if I exert 1 Newton of force on an object for 1 meter, I've done 1 joule of work on it, or transferred 1 joule of energy to that object. 1,000 joules is known as a kilojoule, as another common unit of energy. And here in the United States, we use calories, and actually what we use is this one down here. But let me start off with what a lowercase c calorie is, and that is the amount of heat energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So a calorie of energy, if I had a little old gram of water, and I pour that gram of water into a beaker, and I wanted to heat it up, and I wanted the temperature to go up 1 degree Celsius, however much energy transferred from the Bunsen burner to the water to raise that temperature by 1 degree Celsius of that 1 gram sample of water, that has been defined as a calorie of energy. A calorie of energy. How I can relate the energy, calories and joules, okay, as a little side note here, 1 calorie is equal to 4.18 joules. I'm going to use that conversion here in a second. And then the other calorie that that we're all familiar with is the calorie that we see on the side of our Snickers bar, and that calorie is not in fact a lowercase c calorie. It is in fact a uppercase C calorie, which is 1,000 calories. So 1 calorie, a food calorie, is enough energy essentially to raise 1 gram of water by 1,000 degrees temperature, or 1,000 grams of water, 1 degree. That's going to be the amount of energy associated with 1,000 lowercase c calories. Okay, so how are we going to use this energy in heating or cooling a substance? So there's 2 ways that we're going to talk about today about heating or cooling a substance, and in order to do that, we need to talk about something called specific heat. So specific heat is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So a moment ago we talked about the calorie, and the calories amount of energy specific for water, but specific heat could apply to any substance, not just water. It's the amount of heat energy needed to raise that substance, if I had a gram of it, by 1 degree Celsius. So imagine that little example I did a second ago, but instead of water in a beaker that we're trying to heat up, it's some other substance here. Okay, whatever that might be. So our formula for this is going to be Q is equal to MC delta T, where, okay, this is going to be our formula here, where Q is the amount of heat energy, okay, amount of heat. This can be positive or negative, depending upon our change in temperature. M is the mass of that specific object we're talking about. C is the specific heat. Okay, also known as the specific heat capacity. And also we have delta T. We saw this in gas laws. This is the change in temperature. Okay, change in temp. Always final minus initial. It's not the other way around. Okay, it's always final minus initial. That's how we can have positive or negative heat values. So this is one of the forms for an equation involving specific heat. Now, if you rearrange for C, you can, of course, get an equation just for calculating the specific heat of a substance. And so our units are going to be, we can either have specific heat in calories or specific heat in joules. So if I have an example, let's say of H2O, okay, for water, we said the specific heat, water is actually, the definition of a calorie is 1 calorie. The specific heat of H2O is 1 calorie per gram degree Celsius. Okay, you'll notice the units on there. Calories and then divided by grams divided by degrees Celsius. If you rearrange C by itself, those are the units left hanging that don't cancel. What does that number mean? It means that if I have, you can put a little 1 down here, it's totally fine. If I have 1 gram of a substance and I want to raise it 1 degree Celsius, it takes 1 calorie of energy. And if I wanted to look at the specific heat of water in joules, we could do a little bit of dimensional analysis here. We said 4.18 joules is a calorie. And when I cancel my units, 4.18 joules of energy is also going to raise a gram of water a degree Celsius. Now this is just for water, specific heat for water. If I wanted to raise a gram of water a degree Celsius, I'd have to pump in 4.18 joules, which is the exact same amount of energy as 1 calorie. They're just different units. So I have a little example here. How many joules of energy is needed to raise 5 grams of water by 10 degrees Celsius? Gives me the specific heat of water. So it's asking for how much energy is needed, and we have some givens here. 5 grams by 10 degrees Celsius. Okay, there's a change in temperature, and we can go ahead and plug in what we know. Okay, so Q is equal to question mark. Mass is equal to 5.0 grams. Change in temperature is always final minus initial. If it goes up 10 degrees, let's say it was at 110, and it goes up to 120, 120 minus 110, that's a positive change in temperature. Okay, it was a positive change in temperature. So delta T here is 10 degrees Celsius, and C for water is 1 calorie per gram degree Celsius. So in order to solve for the Q, we can set Q is equal to MC delta T, and I can solve for my unknowns. 5.0 grams divided by 1.0 calories per gram degrees Celsius times 10 degrees Celsius. Oops. You'll notice my units of grams, gone. Units of degrees Celsius, gone. I'm left with Q in calories, which is beautiful. So 5 times 1 is 5, times 10 is 50 calories. Okay, that would be how much energy I would need to raise 5 grams of water by 10 degrees Celsius. Okay, beautiful. Let's keep moving. So this is something called heat of fusion, or enthalpy of fusion. And heat of fusion is a very specific amount of energy, and it's associated with melting a certain amount of solid, and I put in bold here, or freezing a certain amount of liquid at its melting point. Okay, so I'm going to use a water as a great example. Okay, so heat of fusion, how much energy I need to melt a certain amount of a solid. Okay, so let's say I have some nice ice here. Ice, there it is. It's at 0 degrees Celsius. Okay, it's some chilly ice at 0 degrees Celsius. It's at the melting point. That's important. We're talking about ice at the melting point. So if it was really cold ice, it's been heated up to 0 degrees Celsius, its melting point. And if I put a pump a little bit more energy in here, we have delta H fusion. Okay, that amount of energy that I pump into this thing, let's say I have a gram of ice, that's going to cause this ice block to melt. And when it does that, I'm going to have a puddle of water, which is also at 0 degrees Celsius. So to do this, to melt ice, it actually takes energy. Where does that energy go into when I melt my ice? Melting ice. It turns out that for water, the heat of fusion of water is 334 joules per gram. Okay, for water, it's 334 joules per gram. So if I had a gram of ice and I wanted to melt it, I'd have to pump in 334 joules of energy. Now I look at to the right, and the temperature is the same, so where did that energy go? Well, it takes energy to break those bonds. We have to break the intermolecular forces. Those bonds between water molecules, it takes energy to do that. Okay, so we break some bonds, and when we break those bonds, we can turn our ice into water. And so the equation that we can use to calculate this amount of energy associated with this is Q is equal to M delta H fusion. So in order to find the amount of heat needed to melt a certain substance, we need to know how much substance was there and the heat of fusion for that substance. And we can multiply those out and get a value of heat that it would need to take a certain sample. Now you also notice I put in parentheses here, or freezing a certain amount of liquid. The reason why I do that is this amount of energy here, 334 joules, that's a positive number associated with melting ice. However, if I were to freeze ice again, it turns out that if I were to freeze ice and go back the other way, it's going to produce energy, and it's going to produce energy to the surroundings, and it's going to produce 334 joules of energy, and that would actually be a negative change. But it's the same amount of energy. Whether I freeze or melt, we're going to have the same exact amount of energy transfer. So I put that in parentheses there. And it must be at its melting point. Okay. One last little piece here. We're going to talk about something called the heat of vaporization. Okay. So while we're at it, let's say we have our puddle of water. I throw it in a beaker, and I heat it up all the way to 100 degrees Celsius. Okay. So let's say I have my water again. And I want to vaporize this, heat of vaporization. And I want to turn that water into steam at 100 degrees Celsius. So in order to do this, it's going to take energy. all those molecules of water that are connected to each other with hydrogen bonds, we're going to need some energy, heat energy, to break apart those intermolecular forces. So as we add heat, okay, as we add this heat of vaporization, we're going to break intermolecular forces, or those bonds, okay, hydrogen bonds in this case. We're going to break those bonds in order to vaporize my liquid. And so for water, the heat of vaporization for water is equal to 2,260 joules per gram. Okay, it takes a lot more energy to vaporize than it did to melt it. And so there's our heat of vaporization for water, and an equation for heat of vaporization. To find that amount of energy, we need to know how much substance is there, as well as the vaporization, heat of vaporization of that substance. Alright, this has been an intro to some ideas that we're going to be using in the next couple of days, and I hope that this was helpful.